Welcome back from back time. Our next talk will be on the interplay between stars, ISM, and the environment, unresolved scale.
Which is highly relative, as we've all been discussing. So hi, everyone. I'm Milena Foscindiere. I'm a postdoc at Stockholm University. And I'm going to give a very brief introduction. We've all been talking about the process of star formation. And this is sort of the general view that we have of it now. But I think a very important question that everyone's kind of after is how does it fit in environmental differences? So is this process the same everywhere within a galaxy or even across different types of galaxies? So the first part of the talk, I'm going to focus on systematic differences of the initial conditions of star formation, so molecular cloud properties. And then the second part will be more on the actual onset of star formation and the start of the stellar feedback processes. So to look at molecular cloud properties, we wanted to use high-resolution data, of course. So for that, we developed a new imaging technique, which uses Hubble Space Telescope optical data and really uses these dust extinction lanes that we see really prominent in, for example, the V-band. And it's not a traditional extinction technique. Instead, it's more of a contrast. So we measure optical attenuation by comparing the observed light of the galaxy to a sort of reconstructed stellar light map. Assuming a sort of sandwich-like dust stars geometry. So we assume that the dust is sitting close to the midplane of the galaxy, and then you have a foreground layer of stars and a background layer of stars. And comparing these two essentially allows you to get how much dust is causing the observed extinction, and then from that you can translate that into gas surface densities. So we do calibrate this using Herschel far infrared dust emission at lower resolution, and this is to just generally ensure that the dust masses we're getting from the extinction technique are consistent with the emission. So this is what the map looks like from 51, which was our test case. It looks a lot better in that screen. So we get close to the Hubble resolution, so 0.14 arcsecond, which translates to about 5 parsec resolution for the whole disk of M51. And here I'm just comparing to the beautiful CO map from PAWS, which gets 40 parsec, and I hope you can appreciate the difference in the resolution achieved here in these zoom-ins at the bottom. So now that we have this fancy new imaging technique, which we can get sub-arcsecond resolution for nearby galaxies, let's look at molecular cloud properties versus environment. So for that, we picked a small but mighty sample of nearby galaxies, where we range from grand design spiralos to some barred galaxies, as well as a flocculent, again, to look at systematic differences in the initial conditions of star formation. We extract molecular clouds from all of these galaxies, and at the native resolution of each galaxy, we get about a sample of 99,000 clouds total. So looking at cloud properties, for example, cloud surface density, here I'm showing you the distributions of these values in the centers versus the disk of these galaxies. So you see generally this agrees with what everyone else is seeing, which basically you get higher surface densities in centers than you do in disks, although this difference is slightly smaller in NGC 628. And the distributions themselves also look very different between these two environments. But when you look within the disk, so differences between arms and interarms, this becomes a lot more nuanced. So you see that in NGC 628, for example, the populations look basically the same. There's no difference. But in the barred galaxies, you do see slightly higher surface densities in the arms than the interarms, but there's no really significant difference. For M51, we actually found a radial dependency. So we found that in the inner galaxy, you have much higher surface densities in the spiral arms than in the interarms, and also a much higher spread of values. But when you go to the outer galaxies, suddenly the populations look very similar in terms of surface densities. And we think this is an observational signature of the interaction of M51 with its companion, which has been hypothesized for a while that is actually affecting the spiral pattern of the galaxy. we also see some differences in radial trends in the bars of these galaxies. So again, I'm showing cloud surface density. You see that for 1566, we get a bump in surface densities towards the bar ends, and a corresponding increase in the arm surface densities and interarm. Whilst for 4321, you have an increase in surface density right at the center of the galaxy, as well as in the bar ends, but no significant increase in the spiral arms and interarms. And this could suggest, of course, that there are different dynamics undergoing in these bars, different bar-driven gas flows, which is something that we want to investigate further with dedicated simulations of these galaxies. Okay. So then what we did is sort of what is common to do in the field of molecular clouds in nearby galaxies specifically, which is you put all of your galaxies at the common resolution so you don't have a biasing effect. And then you look at all of the clouds within a given environment. So again, I'm showing surface density, and you see the general trends remain. You get higher surface densities in the centers than disks, and then a small difference between arms and interarms. But if I had just done this, and of course, we have a small sample, so we could afford to look at each galaxy individually, we would have lost on a lot of what could be interesting galaxy-to-galaxy variations. And in fact, when we do these environmental qualifications, the underlying assumption is that all spiral arms or all bars are behaving and affecting the ISM in the same way, which is not true, really. We see the arms in SGC 628, for example, look very different already from M51 or 1566. So we should move away, perhaps, from these qualitative environmental classifications, and maybe instead look at molecular cloud properties as a function of more physically driven quantities, things like midplane pressure, shear, torque, which is already work that's being done. Okay, so for the second part of the talk, I wanted to introduce the FEAST project, which stands for Feedback in Emerging Extragalactic Star Clusters. Here's a hopefully comprehensive list of everyone in the team. And you've already seen some of these images float in some of the talks this week, which has made us really happy. So FEAST is trying to really pierce into the sort of hidden stages of star formation, the really young stages, which have really been practically inaccessible at the resolutions needed before JWST for nearby galaxies. So we selected a sample of galaxies within 10 megaparsec, again ranging on different morphologies. We have some grand design spirals, a barred galaxy, we have a low metallicity dwarf type galaxy, as well as an interacting pair. And we imaged them with JWST. Wow! So you can see these really, really beautiful data with NIRCam and MIRI. And so, as I said, our objective was to look at differences, at the hidden stages of star formation. So for that, we've set out to hunt for these emerging young stellar clusters. I did not say embedded, I said emerging. And so we've done this for all targets, and we've classed these stellar clusters as EYC1s if they are compact emissions in the hydrogen recombination lines, so Paschen alpha, bracket alpha, as well as having some compact 3.3 pH emission. EYC2s are just the hydrogen recombination lines, no Paschen alpha. Then we also select some compact pH peaks. And then we also grab some Legis optical clusters, which are younger than 10 meg a year. And I should also point out that this paper went on arXiv today, so you should look at it. Okay, so from our catalog of stars and our work on MEDI3, we've put all of the selected EYSCs into these color plots. So you should read this y-axis as sort of going down, no, other way around, going up in age. So older stuff is down here, and then you get more pH as you go towards the right. And you see that as we go from EYC1s to EYC2s to the optical clusters, you go up in age and down in pH. So this 3.3 micron pH is thought to be very susceptible to radiation or feedback. And so we think that this is evidence for an evolutionary sequence where you start having from EYC1s to EYC2s to optical, they're slowly emerging from the natal cloud. And you can also see this with the Paschen alpha, because Paschen alpha is thought to trace really young stellar clusters. So you go from the younger to the older. But really, for more, please see Alex's talk, which is the last one of today. He was more involved in this work, as well as presenting some emerging timescales. As for when I'm directly involved, so we also got cycled to near-spec MOS data, so multiplex spectroscopy in the 1 to 5 micron range of hundreds of star-forming regions in NGC 6 to 8. And here's some preliminary spectra. I hope you can tell how beautiful these are and how just the sheer amount of lines, as well as the 3.3 micron pH feature, which we see already some variations, but that's undergoing work. And this wavelength regime is actually fantastic because it gives us a lot of diagnostics for early stellar feedback. And with that, I come to the end of my talk. Here's the summary, and I also wanted to say, as I've already mentioned, that there are dedicated simulations in the works for all of the galaxies that I image with the HSD extinction technique. So if you want to see all of our work, please scan the QR code. Yeah.
We have plenty of time for questions. So, questions? Can you go back to the? Oh, did you have?
I do, yeah. I'm thinking about this relative to Christina's beast extinction mapping, which you can't do at these distances, but you can do in M31. And so, like, you have the cross calibration with Herschel for this, but there's resolution mismatch there, which limits how, I guess, neatly they can converge. But if you were to apply this method in, like, the fat data of M31, you could cross-calibrate the stellar point AV measurements and Christina's beast work and the fat beast work and get like a really precise high-resolution calibration between the two, which they can really apply to far away things, and then really know what they're doing. That's the sort of thing you are considering.
Currently, no, because so we are currently only applying this extinction technique to face-on galaxies because of the dust stars geometry that we have to assume. So because we assume that the dust is sort of in the midplane of the galaxy, as soon as we have something inclined, this isn't physical, right? So yes, this could be done. I would just have to go and tweak how we do the geometry bit, but it's definitely something that could be.
M33 might be more. Yeah, 33.
Yeah. Yeah. Okay.
Yeah, why don't I get you and then Janice?
So I was just wondering, could you walk us through a little
Louder?
bit more in detail how the HST extinction technique works?
Sure. So essentially, I go back to that one. So we have the original image where you have all of these prominent dust lanes, and then you have what we reconstruct as a stellar light. Essentially between here and here, what we do is we remove as many bright point-like sources as possible. And then we sort of median filter the image to try and interpolate over the extinction features. So then this is what I mean when I say it works as sort of a contrast. And then by assuming that you have the dust close to the midplane of the galaxy, we're essentially solving the radiative transfer equation, assuming both an emission and an absorption component, if that answers your question.
So here your foreground and background looks almost exact.
It's the exact same, it's just that this is a fraction that's in the front, and then a fraction of it is in the back of the dust.
Janice?
Yeah, so the extinction mapping, have you compared it with other measures of the extinction of the galaxy to see how what the differences are?
So it's tricky. From 51, we did do some. The problem is that those are usually done. For example, one that I can think of is where you have H alpha, like bright H alpha to do the extinction. And where there are really bright optical sources, I don't see extinction, even though we have that step of trying to remove these bright point-like sources. So I did a sort of general estimate with the literature, and they seem to correlate, but it's difficult to do it precisely because of this limitation in the technique.
So it seems like HST, unless if I understand this correctly, it seems like the HST extinction mapping technique is monochromatic.
Yeah.
Have you tried doing this in multiple bands and also measuring the extinction curve?
No. So, well, I've done it for the B band as well, just to sort of test if it would work. They agree pretty well. I think there was a slight, it wasn't exactly one factor, it was like 1.0 something. But I haven't looked at something like that, no, the extinction curves.
David?
Yeah, so I'm curious with the extreme wealth of detail you have in your near spec observations, do the four categories that you established from the broadband work, do they get additional information? Are there transitory phases between those? I was actually going to suggest, I don't know if you know the tool that Brice Menard put together, the sequencer. It works wonderfully with spectra like this to put them in, each one next to its most similar object, and you could get a wonderful sequence, I'm sure, out of it.
Oh, okay, I'll definitely talk to you about that later. So this is very hot off the press, finished with data reduction sort of thing. So that's something definitely that we are looking at. One thing actually is that obviously we did these observations with already a photometric catalog of EYCs, but then when we actually got the data, we realized there's a lot more sources in the spectroscopy than we were able to pick up with the photometry. So it's a lot of so we get about hundreds of these slits that we opened, and we're seeing an average of 3 stellar clusters per slit. So you can see that's going to take me a while to go through all of them. But yeah.
Okay.
I love these spectra.
Thank you.
Oh my God. Using the MSA like this is so cool. I both envy you and don't for having that.
I will just brag a little bit. These are just over plotted on top of each other. I haven't combined the grisms actually. So I was really surprised that they match.
Good job. Good job. I do actually have a question, but since it's very preliminary work, you may not be able to answer it. So the 3.3 over 3.4 aliphatic is going to be such an interesting test of your evolutionary sequence. Have you done anything looking at that?
Yes, so that is definitely the plan that we're doing. So we're using a cafe developed by, is it the Goals team? I think it is, that Thomas very kindly gave to us. So that is definitely in the works. So I'll be fitting all of these and then comparing the actual ratios between the two components. Yeah, definitely.
Eager to see those.
More questions? Thank you. So in Jimenez's work, one of the interesting findings was looking at the equivalent with H alpha as a tracer of the age, comparing it to optical clusters to establish an age sequence. So this is not necessarily something you need the spectra to do because you had the imaging before. I wonder if you saw a similar change in hydrogen line equivalent width per your stages.
That is a question that Alex will be answering in his talk. So I will put him in the fire line. Yeah.
Any other precursor questions? Okay. Thank you all again.
Thank you.
Did you turn on?
I like.
There's a little switch right at the top.
Spin too fast. We can mention them.
Okay. Our next talk will be by Kiana Henney from Wyoming. SED modeling star clusters using direct markers of gas and dust emission with the FANGS catalog.
Hi everyone. I want to start off by thanking the organizers for putting on such an awesome conference. It's like maybe the best conference I've ever been to. First of all, also my whole FANGS team, which has many, many people. As you guys have all heard, the FANGS HST JWST dataset is composed of 19 galaxies. I'm only using 17 galaxies for this project, with 10 filters with comparable resolution from the near UV to the near IR. This is including broadband filter, like stellar broadband filters. We got HST H alpha, and then the NIRCam dust continuum and the 3.3 PA emission feature. And the sample that we are using in this work is about 6,000 human classified clusters. So these were classified in the V band by Brad Whitmore. And then we model these clusters with Sgr A. And so the goal of this project was to quantify the impact of the inclusion of NIRCam filters and then the matched resolution H alpha directly into SED fitting and see what impact that has on age, reddening, and mass. So just as a little brief overview, so when we're doing SED modeling of star clusters, one of the biggest problems that we run into is age, reddening, metallicity, degeneracy. So there are many combinations of these that result in similar types of solutions. And so we can see here, we've got some young reddened clusters, and then we've got some old globular clusters, and you can see in the optical, they're very similar. This is all normalized to the I band, by the way. When we add H alpha, suddenly they are, they're very distinct. And so this is great. When we add NIRCam, we can see that, yeah, H alpha is a great marker of kind of the difference between these two populations. But there are more degeneracies. So, this one may have solved the one between young and old solutions, but there are more. So we start off by separating out our clusters into 3 categories that have sort of different physical qualities. So we've got our young gas-rich clusters, which I'm going to talk entirely this talk is about. Then we have old globular clusters, which we select with a whole detailed method that you can read about in Thilker et al. And then we've got general clusters, which are assumed to be, they're everything else. So they're assumed to be approximately solar metallicity, and they can really be any age. What we did is that we used an H alpha equivalent width to identify which clusters have a significant fraction of high energy photons being absorbed and re-emitted through nebular lines. So the question is not just, what has H alpha, but, is that cluster the source of the H alpha? So here we have 3 example clusters that kind of exemplify different elements. So at the top here, we have a cluster. We can see it's got kind of a red optical slope. It's got really strong H alpha. It's got near IR dust emission. It's got a PA feature. When we look at it, it's super compact. It's in this young part of the color diagram. So everything about this says that this cluster is young and definitely has a lot of gas. So we want to fit that one with nebular emission. But this middle one, so it's got a blue optical slope, so it's probably young also, that makes sense. But you can see that the region, the colors are red is H alpha, green is the 3.3 filter, and then blue is stellar. So you can see that this is a quite complex region. And there are many stars, star clusters, associations in this region. So even though it has H alpha, we don't know for sure how much of that H alpha is coming from this cluster. So this guy, it doesn't have enough H alpha that including or not including it is going to make a big difference. And so we're just not going to include it. And then on the bottom here, we have a cluster where including H alpha could be deleterious. So it's got a more red, a red optical slope. It doesn't have any signs of hot dust emission. It's got a little H alpha, but you can see that this area is also very complex. We don't know where that H alpha is coming from. And so we empirically derived this threshold of 80 angstroms that is basically above which where you can be pretty confident that those clusters are a primary source of nebular emission, and below which it's just kind of hard to tell. So this is our overall results. On the x-axis, we've got modeling with just HST filters, and on the y-axis, we've got when we add NIRCam. So you may notice some interesting features. One of them is this chimney. Is that a mouse? Okay. This kind of like spur where you were fitting a young solution, and then you end up with an older solution. And then also another thing is that we seem to have a lot of clusters that were modeled with higher reddenings and are now modeled with quite low reddenings. So here are two kind of like example clusters in these two categories. So everything red is fit with HST only, and everything blue is fit with HST and NIRCam. So in this top example, this is an area where we can see that adding NIRCam is really, really helpful in finding a more accurate solution. So, when we were just looking at these optical filters, you could think maybe it is a reddened young cluster, and indeed the HST solution is young and reddened. But when we look at kind of all these different metrics, that solution, when we add NIRCam, it doesn't really hang together. So we can see that there's no hot dust emission. So this cluster does not have natal dust, close by that it could be heating. And then when we look at the image, it's pretty isolated. So this is a cluster that is in this area that is prone to degeneracies. So it's right around here. I'll show another slide in a minute, where you could hit this kind of like 10 to 100 area, or you could hit this like 5, or go all the way to like 1 to 3. And so you can really see that adding NIRCam is very helpful. Now, another area that is kind of interesting is this bottom cluster. So, this one, it's not a question of exactly what age it is. It's definitely young. It's in this blue part of the color diagram. You can see there's H alpha surrounding it, and it's got this, continually blue opticals or blue slope all the way through. But one thing that's interesting is that there's no hot dust, and it is right here in the middle of this track. So if you add reddening, it doesn't have a lot of reddening. It may have some foreground reddening, but it's unlikely to have a lot. So how does it get to this track? So we have a lot of clusters in this category, and I would be happy to talk about those with people that are maybe showing that the stellar model we're using, this is the Bruce and Charlotte 2003 model, maybe has some weaknesses in this first 10 million years. So here's a little more about those clusters where we are breaking this young intermediate degeneracy. So you can see they're all in this area where there's a bunch of solutions. And this isn't only an optical diagram, and so it doesn't show that at NIRCam, it's really definitively saying that these things are older. So we've got a bunch that move to an age of greater than 50 million years from an age of 1 to 10 million years with only HST. And then we've got some more that move to an age of between 20 and 50 million years. So this is one of the pretty cool things about, this is what we get when we add NIRCam. Another finding is that like a lot of people have been finding with JWST, the smallest pause, the 3.3 pause, are depleted in our young gas-rich clusters. So here's a sample of some of my favorite clusters. This one is my favorite cluster. And when we look at these in sort of SED space, we ended up actually interpolating a bunch of low QPA values. So we're using the drain dust models, and they only, they have the lowest value, 0.47. The next highest value is 1.77%. And what we really find is that in our HST selected clusters, the 3.3 PA feature is really not big. So if you can kind of see this blue solution, this is the QPA of 1.77, and you can see that it has a pretty sizable modeled feature. And when you look at these are like the most reddened cluster, or most dusty, gassy clusters. They have really high H alpha, and they don't have that big of a bump. So we interpolated these values. Now this is consistent with the findings in the Milky Way that are showing that the 3.3 feature is depleted super quickly, and also what Helena just talked about. And so this is indicating that our HST selected clusters are, even if they're not resolved, so like this guy, that's not really resolved. Even our least resolved clusters have probably already, formed H2 regions that we're just not resolving. So yeah, that is my summary, and I will take questions.
Questions?
I had a question about the weirdos. You were saying
the weirdos. Which weirdos?
Earlier, yeah. I think you were saying you think they're 10 million year old, but the Broussard-Charlot models are failing.
These guys?
I guess so. Yeah.
Okay, so now we get to see my secret slides.
Secret slides.
Okay. So this is if you plot up all these clusters, I think these are only non-globular clusters. And so if you look at this, blue area of color space, here we have a bunch of different stellar models. And all these clusters are really, you don't see hot dust, dust continuum or even PA emission in a lot of these. And so it's possible that there's foreground, you would expect there to be a little foreground reddening, but you wouldn't necessarily expect all of them to have a lot of foreground reddening. So this is an area that I am planning on working on next, is, why are our observed young clusters not really aligning with any of these stellar tracks?
How do you know that they're 10 million years old?
Which ones?
But doesn't it say up there?
Oh, so sorry. Yeah, so basically 1 to 10 million years is what I meant to say.
Right.
So between 1 and 10 million years.
So why would we expect the Broussard-Charlot models would fit at all if these things are just a canonical IMF? They're evolved stellar populations, right, after the IMF has been established. So if these are young things,
so
I don't know that I would expect Broussard-Charlot to fit.
So when I say young, I mean 1 to 10 million years. Is that what you mean when you say young? Okay. I mean,
this is YSOs that are 2, 3, 4 million years,
Yeah, so this is what I was kind of talking with some people today about, is that when we're talking about 1 million year, when we're looking at clusters that are in nearby galaxies, we can't observe super embedded clusters with HST. So it's possible that, none of our clusters are actually 1 million year. That's a possibility. But we do have clusters that appear to be very exposed, and they are very blue. But yeah, maybe there's nothing up here because everything that would be up here is actually embedded. That's definitely a possibility.
Well, there's models, I think, for population synthesis of YSOs that maybe would be worth looking. I'll try to find a reference.
Yeah, we can talk after. I would love to do that. Yeah.
Your summary slide, you said that you guys aren't resolving, potentially resolving some of the H2 regions. And so I wanted to pose the question of what resolution would you need, do you think? Do you have an intuition for how small or what the limit is?
So we use a 4 pixel aperture, HST pixel aperture, which translates in NGC 628 7 parsecs about. So smaller than that.
Perfect. That's a great answer.
Other questions? Let's see, Becca, and then you.
Have you tried adding the MIRI data to your fits to see if that's any more constraining, or is the resolution just too different?
Yeah, so I have, when we first got this data, I did a bunch of looking at MIRI. Then now I am once again looking at MIRI. I would say that MIRI seems likely to be very useful for our young gas-rich clusters, because when you look at the MIRI, they have extremely coincident and bright MIRI emission. For more, less gas and dust-rich clusters, I think that treating any MIRI measurement as like an upper limit is the most sensible thing to do, because there are dust filaments, there are it's really hard to know whether the dust is associated unless you have a really coincident bright MIRI. But yes, I have looked at MIRI qualitatively, and I am planning on doing more quantitative. Yeah.
Thank you so much for the talk. Is there any case that adding near IR data doesn't help?
Yeah. So I would say, I guess, so there are plenty of cases where it is sort of agnostic, like you can add it, but it is not super, let's see here, helpful. So like globular clusters, for instance, globular clusters don't, from kind of more intermediate ages to globular ages, the near IR does not really evolve very much. And so you can see in this plot over here that, this is a optical color, and then we have a near IR color, and they're like totally overlapping in near IR space. I will say that there seems to be when we look at all 10 filters that I'm using, that it seems like adding those filters is identifying some clusters that are likely to be globular clusters that got missed with the 4 filter bands. So there's all these blue points basically that are in this like globular cluster regime. When you look at them, they seem very consistent with globular cluster qualities, and they have very their goodness of fit is actually a little better when you do the globular cluster solution. So these seem to be it seems to be that when you add NIRChem, you catch a few globular clusters that you didn't catch before. But if you're talking there's no other better 4-color space that is better than UBVI, I would say.
Janice, then.
So this is more of a commentary, but it goes to the heart of what I think one of the main goals of this conference is. And the first one is that Kiana, one of the challenges is how to associate the gas with the heating sources, right, when you're on these scales, because the ISM is just incredibly messy. And then the second point is really reflecting a question back to the audience. And, when we're doing this SED fitting, when you're trying to model gas and stars together, you just introduce so many more free parameters. You have to be really careful about what the goal of the SED modeling is. So if you're bringing in MIRI, for ages, people who are modeling stars have done the stellar part, and then modeling the gas and the ISM have done that separately, and for good reason. So the question is, what do we gain, if anything, by combining the two things? Because it gets to be incredibly messy, right?
Yeah, I actually do think that one of my, let's see here, these guys, I do think that adding MIRI is potentially helpful, because I can talk with this more in detail with anyone, but I actually think that so the near IR is only showing the hottest end of the dust continuum. And so if you have any dust that's not super close by natal dust, that's going to, when you're doing SED fitting and you don't see any dust emission in the near IR, then the best solution is going to be it's got to be no reddening at all. But that's not necessarily always true, because you can have dust screens that could be adding a little reddening. So I do think that adding MIRI is like potentially helping to constrain these scenarios where you have no near IR dust, but you might have mid IR dust. And that could, especially if you have a dust screen, the MIRI is going to have some flux. It's not going to be that bright, but there's going to be some. So I do think that's an area that like MIRI could be directly helpful.
Last question.
Yes. First, I want to thank Janice for that lovely comment. I think that really encapsulates a lot of what the past couple sessions have been about. And to kind of add on to it, like, why MIRI? I have a very direct question on why MIRI. And of course, it's about pods, because I love pods. So how do you know that the grain size distribution of the pods is changing if you're only looking at the 3.3 rather than all the pods? Because there's so many degeneracies in those drain models in the first place, like only modeling one of the features.
Yeah.
How do you know anything?
Yeah, so I guess when I should be more careful when I say like when I'm talking about like QPod, like I'm really talking about like it seems like there are very few small 3.3 pods. So like that's not speaking to the larger pods now. Like some other people have done some work that seems to indicate that they are changing synchronously. I think another important thing to keep in mind is that there is the effect of like the changing ISM is going to be, I think, a lot bigger than the like in a tiny aperture like evolution of the dust in that little space. So like you're clearly blowing out the gas and dust. And so while it, like, you know, the 3.3 pods like do seem to be like most sensitive in like Milky Way work, but also like the biggest impact that we are seeing when we look at, you know, these young gas-rich clusters over time is that they are physically getting rid of their dust. But yeah, I wouldn't take it to mean much, if anything, about the larger pods.
Thank you again.
Thank you.
Okay, in our second talk about SEDs and our second talk from Stockholm, Alex Pedrini will be talking about dissecting the SED of emerging young star clusters. Did you turn on your mic?
I did, yes.
Perfect.
Okay. Hello, everyone. I'm Alex.
I'm sorry, here's your.
Oh, thank
That's
you.
yours.
I'm Alex. I'm a PhD student at Stockholm University. And yeah, today I'm going to talk about like the spectral energy distribution of emerging young star cluster nearby galaxy. So then why emerging young star cluster? And I don't think I need you to convince anymore after today, after the discussion session that we had, that studying these emerging young star cluster is then very important for the emergence sequence, because then becomes really a key proof for like feedback timescale. So we have like that when we have the observed star formation and we have this young star cluster that like the massive star inside and start injecting like a lot of energy in the ASM. They perturb the ASM and then they modify, they perturb the cloud, and eventually they disrupt. And then we see like they open up, and we see like the optical population of star clusters we have been observing for a lot, for example, with JWST. So yeah, this emerging timescale is very important and to characterize which kind of cluster are inside and which kind of cluster are like perturbing the ASM, because then these are really sensitive to the stellar feedback, so also the kind of feedback we are observing and so on. So as Elena already like introduced before, we have like observing like emerging star cluster in like 6 galaxies in the 5th sample. Today I'm going to present you like results on the emerging star cluster population in 4 of these. And so we have like, you see here the population of emerging star cluster in M83, in NGC628, and in M51. And also we have like this lower metallicity NGC 4449. So when we look at the near-infrared color of this cluster, this is like what we're getting. So we're observing basically a beautiful evolutionary sequence, as you can see here, that basically, so the age goes down like this, no? So this is like true for all the galaxies we are observing, and then it's like defined by different evolutionary sequence of these star clusters. So we start with the first one. These are like the EOSC1, as already Elena defined. These are like selected to be very compact in Paschen alpha and in 3.3 PAH emission, 3.3 micron PAH. And these are like basically are clusters that are still like connected with their H2 region, and probably their like PDRs, like the 3.3 micron is doing very well in tracing the PDRs. And might be like this like stage might be like ensemble this like evolutionary stage, you know, of the emerging of star cluster. Then we have the second one. These are like the EYC2 we call. So these clusters are like still very compact in Paschen alpha, but are not associated anymore with like a compact feature from the 3.3 micron. And it might be like a more subsequent like stage in which like these clusters are like start perturbing the cloud, or still like start emerging. And finally, as you see here in blue, these last they're very down in the 110 million year sequence. We have this like what we call optical young star clusters. So these are like clusters younger than 10 million years detecting in V band, so they're optically exposed. And that might like they like their exposure might like resemble the final stage of like this evolution in a sense, no? So, however, this is not enough to like understand like this emerging phase. We need to understand like what the property of this cluster, what are the ages of the cluster, as Chiana also talked a lot, what are the masses of star clusters. So to do that, we did SED fitting using the Sgr A SED fitting code, using both like HST and JWST. We have a lot of band both in broadband, but also we have narrow band lines which are like very useful in tracing the ionized gas. So we can, as you see here, and so with Sgr we can basically model the star emission. As you see here, that we can also have like the attenuated star. This is like a cluster, for example, with an EBV of 0.9. We can also compute we model the nebular emission, but we can also have access to the dust emission of like the star clusters. So we did that for like our sample of cluster. I'm going to present you today like what we found about the EYC1 population. So the one that are still very compact, the youngest one. So you see here, this is like the general result on the 4th galaxy, where like we see here the age. And you see when you look at the mass, that's basically this for all the spiral galaxies that were like kind of well centered at 1,000 solar masses. And we look actually, we have like kind of lower masses for the low metallicity target, and you see for 449. So this is a general result. But then what we did is that we start looking at in detail at each SED. So we start looking at every SED, and we actually end up in like two main issues that we found looking at the SED of cluster. The first one is that the best dust models that we get from Sgr are not constrained by the observation that we have in star-forming region in the far infrared and in the near-infrared and infrared infrared. So the model don't converge in our best Sgr fitting results. The second one is that when we look at like some SED, we observe like observed excess. So the observed here is the blue point. The best fluxes are the red one. And when you look at the 1.5, 2.5 micron range, especially the 150W filter and the 200W, we see a discrepancy in the observed flux versus the best flux from Sgr. And this actually seems to depend on the mass and the age of this cluster. So you see that here, when we go to like a older cluster, a more massive, this like seems to like get down in amplitude. Seems like we have like a less excess in this. So this is like an idea, but then we quantified much better these observational stuff. And so here I'm showing an example in M51. So this is showing like all the filters from the blue on the down on the bottom and the red on the top. And then I'm showing you the difference between the best flux from Sgr, the best value from Sgr, and the observation that we have. And so if it's at 0, then we have a good agreement between model and observation. If it's on the positive area, the observed fluxes are like higher. And we see basically, when you look at the median values for our cluster population, you see basically that these are clear offset from the rest, no? And actually, when we when looking at the younger one and the less massive one, then this becomes very important. So this, you see the square, which are like the less massive one, less than 3,000 solar masses, become much, the scatter becomes more important. Become less when we look at an intermediate age, we get from like 3-6 million years. And actually, when we go to the older one, seems that we don't have any more like this excess. However, when we look at the narrow band, which are the one tracing ionized gas, then we are not fitting anymore. This means that these clusters are actually younger clusters that are like badly fitted by Sgr and are fitted like older objects. And this is not valid also for M51. This is valid for all the galaxies we have studied. So it's valid for 628, it's valid for M83, and it's valid for NGC 4449. Even if for the low metallicity case, this looks like a little bit less the scatter compared to the other. So then we ask what's happening, what can be the sources in the near infrared that are producing that. So the near infrared is dominated by still by star emission. So what we argue can be the reason for this that is not implemented in the, for example, in the deterministic models such as Sgr A and so on, is the stochasticity of the initial malfunction sampling. So this can be an effect in the near infrared, can be important, and you see the distribution of mass. We have a lot of low mass cluster and can have this where this can be important. Near infrared emission from prime sequence stars. This can also be a factor in the near infrared. And finally, we can be also other sources, for example, thinking YSO that emits very hot dust, or maybe other models, like Kiana also was telling before, we need more precise isochron and so. But then we analyze the first two. The first two, we can have a look at those. We use the code SLAG, which can implement stochasticity in the IMF sampling, and can also look at prime sequence star they implement in the stellar models. And we actually see that if you see these are our EYC1, then when we count for extinction, and basically this scatter we observe in the SLAG trials can partially explain this scatter that we observe from the deterministic models in this range of in these wavelengths. So, but of course partially, and then we need probably a lot of other stuff are going in here to explain fully explain this. So I'm saying this in saying we cannot really probably trust the ages we get for single cluster. So what about this emerging timescale? So we implementing another method to go count the emerging timescale of this cluster to become exposed. That was already done before, for example, by Brad. And it's basically a counting method. So basically here we're counting how much EYC, so how much cluster that have already a Paschen alpha associated with this cluster, over the total number of cluster young and at 10 million years, so also the one that have already exposed. And also we can also measure a timescale that is basically only the AC1, so a timescale to already clear the 3.3 microns, so which is much shorter than the total one. And what we're actually seeing is that when we look at the distribution of this timescale as a function of mass, of the cluster mass, if we don't account for this phase, which is we're not complete, then it seems when we basically, here is basically we're putting all the galaxy together, all the population of cluster together. So you call it I don't know, a super galaxy in a sense. And we actually see a clear trend of timescale a decreased timescale as a function of cluster mass. So meaning that higher cluster mass are presenting lower timescale in the exposure to become exposed. We're talking now, we're discussing a lot what are the implications of this, what can be the reason for this, but seems this seems that is be kind of a clear trend in our galaxies. So these last results bring me to the conclusion of this talk. So what I showed you in this 11 minutes is that we have observed a flux excess that is cannot be recovered by the models. Together we cannot recover the dust model. We have no constraint on that, and the model cannot reproduce our SED so far. And this leads, for example, to uncertain age. We cannot really rely on cluster age by single cluster. And but we have demonstrated that if we consider stochasticity in all the evolutionary phases, and also other processes like PMS, but PMS star, but also models, and so this must to take into account when we want to model the SED of very young star clusters. And finally, I show you that this emerging timescale that we were looking for and was the main topic of the main objective of my talk, seems to decrease when we go high in cluster mass. And with this, I'm done, and I'm happy to take any question. Thank you.
Kiana.
For the overabundance of the modeled H alpha, are these emerging clusters? How many of them have optical anything?
Yeah, that's a good point. So, you see already here. So you see here I'm reporting like the number of clusters that are really well detected. So signal to noise higher than signal to noise higher than 3 in each band. So basically the total, these are clusters that we selected to be detected in all the near-come bands. So you see here the number doesn't change. And then you see the number goes down because of like, because we don't have them, so they're not detected. So most of the time we find a lot of clusters that are not detected in optical as we wanted to. I mean, we were looking for these clusters that are still like not exposed, so they're not embedded in optical. So if we look at the H alpha here, like for example, we missed 200 objects, but still like the H alpha is very bright as we were discussing also in these days.
Follow-up question is like, what is the like, how are you measuring the photometry? Like, how big of an aperture are you using?
So for the photometry, we based for the emerging star cluster, we're basically we fixed on the f200, and then we use an aperture of like 4 pixels for the farthest, like for M51 and no, M51 is 5, for 628 is 4, but then we're doing aperture correction using like Moffat profiles and interpolating like the PSF, and so we correct for different scale, for different like resolution. Yeah, that's what we do.
Janice.
So did you look at the equivalent width of the hydrogen line? Sorry.
That's a good, yeah. So I did for like, actually I did look at the equivalent width of Paschen alpha for like this population, because we were interested in understand how much we differ like from the age we're getting from Sgr A. And so I don't, for example, I don't compare the equivalent width in Paschen alpha from the optical catalog that we have, because, I mean, of course, like most likely it's gonna be that the one selected in compact Paschen alpha are gonna be like higher equivalent width, most likely. But yeah, it's something that we didn't do. Probably like we did in other. But however, when we look at the age, for example, in other methods, for example, when you get ages from Sgr A, when we look at the difference between like emerging star cluster and like optically selected star cluster in V-band, we see clearly that the optical one are all there, like in the sense of like 1, 2, 3 million.
Yeah, I mean, the question is in the context of all these uncertainties which our group struggles with. And so having as many independent tracers of the age, for instance, especially in this regime of stochasticity, you can look at the distribution of the equivalent width and look at, where the median or what the distribution, how it changes for your classes to make sure that it's really an H sequence.
Yeah, no, absolutely. So I agree. I think I feel also that when we look at the equivalent width, we also have maybe it's a more direct tracer at the same time. It's still like using models to get to the ages. So that's, I think, is also something that in the regime of the excess that we're observing, and when we break up, when we break into the then we can, I don't know, like we are not super sure, we cannot trust again like the model where we derive the Paschen alpha as at the same, that basically you see that. Yeah.
So for the FANGS people that have struggled with getting ages and stuff, and following Chris's thing, are there cases where adding the JWST observations seem to make it much more difficult and uncertain? And so we're both kind of learning things. So it's interesting to see some of the things that you're struggling with were the same things we were. I mean, for example, that at the 200 and the 150, it's just not quite fitting together. There's something missing there. Along the same lines of what Janice is talking about, I think the more ways we can come at the problem and see. So in general, we're in pretty good agreement on ages. We tend to get younger ages, at least in my paper, and you tend to get 1 to 3, 1 to 4 million years, where you tend to peak at like 3 to 7 million years and stuff. So there's some systematic differences there, but they're not too much different. An example of another method is expansion of bubbles. And so, for example, Liz Watkins, I mean, she's measured the expansion of the bubbles, and if you look, you'll find that her average ages for quite large bubbles, because she's using CO, is like 3 or 4 million years. which is kind of right in between.
Yeah.
So we're on the right track, but there's still some kind of interesting systematic differences between your group and ours.
No, definitely, yes. I would say also that when actually I did some checking, like what we find in the optical population of like, for example, in 4449 in your age that you estimate, and actually when we look at the what we get from Sgr A is the same. We are very good in the ages that, so we have very good agreement. We have a very good agreement with those ages, for example. So that I must say that.
I'll ask the last question. Does BEAST have enough range in metallicity to be able to say anything about the time scale change, emergence time scale dependence on metallicity? So
yes, a good range. I don't know what it is, but for sure we have some. Yeah. So we have like NC4449 is a lower metallicity case. We have like another like lower metallicity. We have another like galaxy like is NC4490 and the companion that are more like interactive. So they're probing a different environment. But so yes, what I'm doing actually is like looking, because this is like all the galaxies together, all the clusters together, but there are differences in between galaxies in the mediates, and that's what I'm investigating now. Like we have less number, we have a less number of clusters, so it might be statistics is less robust, but it's very fun to see the difference between galaxies. Yeah.
No other questions? Then thank you again.
Killed it. Great. Well, that was such an awesome day. Thank you all for your questions, your discussions, your talks, your posters. This was super fun. I think we all earned a drink after this and some yummy food. So let's head to our house for unbanquet. As I said before, we give like an hour leeway, so you guys are welcome to go back to your hotels, drop your stuff off, take a breather, or if you want to like chill out here for like about a half an hour, we're all gonna walk down to our house together. Please come to me if you need a ride for any reason whatsoever. A couple people that are going to be driving down, including me. Okay, great.
So walking group leaving at 5:30 from the front steps.
Yes, walking group leaving outside 5:30.
The direct cause the application.
So that's different from creating population. It's probably not just simple extinction. You've got a scale near it. Yeah, it's really set up to do all stellar. There are a bunch of codes.
Oh yeah.
Sorry, there weren't that much.
Yeah, well, that was. Are you going to see? That would be So, but I really want to. I went to.
So, and then he runs it through cloud and stuff, and gets.
So we've done this. So I've got rid of the dirty model, and we've got a grid of things that would be like clusters and public shells.
You may be using yours. I should go back and look. But my paper came out in March, and I reference it, and I compare some of those models, and his time scale. But I don't have much background in whether his models are things that are generally accepted or known.
I don't know the models. You send me an email with a paper I can look at and give you an opinion.
I'll probably do that stuff.
But I just haven't.
I mean, the other main thing we were talking about.
I know, so like I was like trying to look for like a notebook.
They're expanding. That's industrial average.
Yeah.
Pretty quickly.